Here's a matrix A given as 2, -3, and -2, -3. And the question is to find the general formula for A to the nth power. Now, some of you might be wondering, like, who cares? Like, why would we want to do that? Well, you've seen this in some other math, which is the differential equations. So, for example, if you had the system of, don't write this, I'm just trying to motivate why we would want to solve such a question. So if you had a system of equations like x1 prime equals to 2x1 minus 3x2, and then x2 prime equals to negative 2x1 minus 3x2, then we rewrite this as like x prime equals to 2, -3, -2, -3, x, where by x I mean x1 comma x2. You write it like this, and you kind of see the analogy between this one. So this, you can even rewrite this as like ax. Analogy between this differential equation with this differential equation. Okay, let me see who remembers calculus 4 here. What's the solution to this equation? Let's use the independent variable as t. So give me a function of t, y of t, that satisfies this. So it's some kind of a function where if you differentiate, a just pops up. What could this be? A times itself. Okay, if you don't know, then let me give you an even simpler question. What about the solution of this? What's a function if you differentiate doesn't change?
E to the x.
E to the x, or e to the t, right? So e to the t prime gives you e to the t, so that's the solution. How about this one then? They're cousins, right? Very similar. What's the solution to this?
E to the at.
E to the at, right? If you have e to the at, if you differentiate, what happens? A e to the at, right? That's what it is. Of course, there could be some constant in front. Same thing here, there would be some constant in front. So you look at this and say, hey, if there was a way to take x as e to the capital AT, then wouldn't you be able to differentiate this and get a times e to the AT? Right? Yeah. So after this, you just say generically, the answer is x equals to e to the AT times C1 and C2, or C1, C2 are the two constants, just like where you have this constant. Here you have constants. That's what you did in differential equations, okay, or calculus 4. Yeah. But then this is kind of weird. How are you supposed to exponentiate a matrix? Does anyone know how to do e to the a? How do you do this? Okay, raise your hand if you have no idea. I've never seen this. Okay, so you've seen this? Who's seen this? Taking the exponential of a matrix. Okay. You guys are no fun. You have to say yes or no. All right, so e to the x is 1 plus x plus what? 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. What is this thing called?
Taylor series.
Yeah, it's Taylor series, right? So how would you define this? Well, you can't have a constant because these should be, like, the other guys are, it's clear what to do here. Right? But then since all of these are 2 by 2 matrices, like here, you need a 2 by 2 matrix as the constant term, so you use the identity as the very first guy. Okay? Now surprisingly, So there's something that you should check. If you differentiate this, if you differentiate 1, what do you get?
0.
If you differentiate x, what do you get?
1.
What do you get if you differentiate x squared?
X.
2x, and then 2 cancels, so you just get x. You're right. And then how about this one? 3 comes down. What's 3 over 3 factorial?
1 half.
It's just 1 over 2 factorial, right? Oh, so what's happening? If you differentiate this, what happens?
It's the same.
It's the same. Now, is that good or bad?
Good.
Why is it good?
That's what we would expect.
Because e to the x is that exact function where if you differentiate, you get the same thing. So if you're claiming that these two are the same, then the right side should have the same property. If you differentiate, you get the same thing, right? Okay. So that can kind of give you some, I mean, it might convince you a little bit that this is indeed true. If you want better proof, then start plugging in some values like 0, 0.1, 1. See how the two are different, and you'll see that the right side gives you almost the same answer as this, and you get better accuracy as you go further along, okay? All right, so that's what we have, and as you can see, in order to calculate this, you need a squared, a cubed, a to the 4th, a to the nth power in general. So you do need to know how to do that. And that's why you actually learned in differential equations. Always the problem with these calculation-heavy courses is that you guys just know how to pass the test and actually not learn anything from it. It's really these ideas that's more important. If you see the idea, then you can enjoy the beauty of math. I don't know what you're trying to go in, what field you're trying to go into, especially those who are trying to become teachers. I hope you understood rather than knew how to pass the test, because only then you can convey that idea to the students. All right, so hopefully that was a good enough motivation for answering this. But if you try to tackle this question directly, you're going to give up very quickly. So look at this. 2, -3, -2, -3. Let's say I want to know the square. How do you do that? You just multiply by itself twice. And then you do a cross down. 2 times 2 is 4. -3 times -2 is 6. 6 plus 4 is 10. 2 times -3 is -6. -3 times -3 is +9. 9 minus 6 is 3. Okay, -2, +2. So that's 2. +6 plus 9 is 15. Okay, do you think you can find a pattern? I don't think so. I mean, this is already big, and even if you use the computer to calculate this, if you use a calculator to do this, you'll be hard-pressed to find any pattern. So if you wanted the 3rd power, then you would have to multiply it to this, another one of these, and I'm giving up already. But you might be more persistent and try this and then give up. At some point you'll give up, okay, because this method doesn't work. Okay, so instead of this, what else should we do? So let me first give you an idea of the solution. So the idea is that you want to rewrite A so that this looks like some 2 by 2 matrix times a diagonal matrix A, B, and then 0, 0. And you call such a matrix a diagonal matrix, right? If you only have numbers on this direction diagonal and everything else is 0, that's called a diagonal matrix. And then P inverse. Okay. So if you can find A as some 2 by 2 matrix times some diagonal matrix times P inverse, so then a to the n, let's call this d, okay? So that's like p d p inverse to the nth power, which is like p times d p inverse p times d p inverse. So this is like multiplied to itself many times. And the thing is, because multiplication of matrices are associative, P inverse and P, whenever they're multiplied immediately right next to each other, then they cancel. So all of these P's in between cancels out, and you just have D, n number of multiplications. So you end up with P times D is this matrix A0, 0B to the nth power P inverse. That's what you get. Now, question, can you cancel this P inverse with this P also? Why not? Because matrix multiplication is not commutative. Okay? If matrix multiplication was commutative, then you can switch this around and you get an even simpler answer. But unfortunately, these two, because it's not commutative, they still survive at the end. Okay? But at least when you take the nth power of this, you get, see, diagonal matrices are very simple to multiply. A0, 0B. What's this? If you square. You do across down A times A, 0 times 0, so you get A squared. A times 0, 0 times B gives you 0. 0 times A, B times 0 gives you 0. And then across down, 0 times 0, B times B, that gives you B squared. And in general, if you take any nth power, you end up with A to the nth power 0, 0, B to the nth power P inverse. Okay? So that's how you are going to solve this. All right. So what we've done is we've changed the question of finding the nth power into question of writing down A as a conjugate of a diagonal matrix. Okay? Now, oftentimes, this is written as, often we write P inverse AP equals to D, and such a thing is called a diagonalization. Called diagonalization. So if we can diagonalize, then we can find out the nth power. Okay, solution. How do you diagonalize a matrix? Well, you learned that if you find distinct eigenvectors for a matrix, then you can diagonalize. So we're going to find the eigenvectors and eigenvalues. So let's find out the eigenvalues. That's the equation for eigenvalues. If you forgot what this was about, you're supposed to subtract lambda off the diagonal. The other ones don't change. Only through the diagonal you subtract lambda. And then you get, and this absolute value means that it's the determinant. What's the determinant of a matrix ABCD? AD minus BC, yes. So I'm going to do ABCD, and then you're going to do AD 2 minus lambda times negative 3 minus lambda minus BC, negative 3 times negative 2. Okay? And And I can multiply this out by just simple foiling. So 2 times negative 3 is negative 6. 2 times negative lambda is negative 2 lambda. Negative lambda times negative 3 is positive 3 lambda. Negative lambda times negative lambda is plus lambda squared. Negative 3 times negative 2 is 6, and there's a minus, so it's minus 6. And if we simplify, this is lambda squared plus lambda minus 12. We look for two numbers that multiply to negative 12, add to 1. Those are 4 and negative 3, so this factors as lambda plus 4, lambda minus 3. Okay, therefore we find that there's the lambda equals to negative 4. Okay, we're trying to set this equal to 0, so we set lambda plus 4 equals to 0. That gives you lambda equals to negative 4. Lambda minus 3 equals to 0. You get lambda is 3, right? So those are the two eigenvalues. Now we have to find eigenvectors for each one of these eigenvalues. So let's try that. The eigenvector equation is to plug those numbers back into the matrix as 2 minus negative 4 would be positive 6, minus 3, and then negative 3 minus negative 4 would be positive 1, and then you're going to have two unknowns. By the way, these two ABs are not the same as that AB, sorry. These two numbers A and B are really going to be lambda 1 and lambda 2. Okay? So this will be lambda 1. The second one will be called lambda 2. Okay? And once you plug this into this left side, put the vector that you're trying to find and set that equal to 0, 0. That's known as the eigenvector equation, right? And if I multiply top and bottom, across down, 6a minus 3b equals to 0. Across down, that's negative 2a plus b equals to 0. Now, of course, 0, 0 is always an answer to this, but we're looking for a non-trivial answer. 0, 0 is not considered as an eigenvector. Eigenvectors are non-zero vectors that satisfy this. And if you divide the top by negative, if you divide this by 3, you get 2a minus b equal to 0, right? And if you multiply this by negative 1, or divide by negative 1, you also get 2a minus b equals to 0. So it's always given. If your eigenvalues are computed correctly, when you plug it back in and you write down the eigenvector equation, you'll always find that the equations that you get are identical. Okay, so that's like one way to check if you're doing your calculation correctly. Okay, now we're looking for simplest numbers that satisfy 2a minus b equals to 0. Can you give me one? Choosing a as 1, what do you get for b?
2.
2. Okay. Yeah, often what happens is, like, if you switch these 2 and negative 1, if you switch those two numbers around and negate one of them, that's a simple way to get the answer. So negative 1 and then 2, so negative 1 comma 2, you negate the negative ones, you get 1 comma 2. You plug in 1 here, you plug in 2 here, you'll see that it indeed solves the equation, right? So you just need one solution. So that says that eigenvector 1 is, 1 comma 2. Okay, let's continue with the second guy. Number 2, lambda 2 is positive 3. If you plug in 3 here and there, you get -1, -3, -2, -6, then put AB equal to 0, 0. And the top equation, if you do a cross down, it gives you -A minus 3B equals to 0. Let's multiply by -1, so it's A plus 3B equals to 0. So you have 1 and 3, switch places and negate one of them, so I guess 3 and -1 should work, right? If A is 3 and B is -1, that satisfies it, so therefore you see that V2 equals to 3 comma -1 is the answer. It is the eigenvector for this animal. Okay, so what do these two identities tell us? Well, it means that A times V1 is -4 times V1, and A times V2 is 3 times V1. After all, what is an eigenvector? It's a vector where if you apply A acts like just the common multiple by a number. That's what it means. Okay? Okay. Now, let me rewrite this. So, I write it like right here again. Okay. So we have 2, -3, -2, -3 times V1, I erased V1. Was it 1, 2? Right?
Yep.
It was 1, 2, right? 1, 2 is equal to -4 times 1, 2. Then we also have 2, -3, -2, -3. 3 comma -1 equals to 3 times 3 -1. And you can rewrite these two into single matrix equation, and that's really at the heart of diagonalization. So you have 2, -3, -2, -3 times, if you put these two vectors side by side, if you write down 1, 2 here, and 3, -1, put them together. So you can see that this is the first eigenvector, this is the second eigenvector. And that's same as 1, 2, 3, -1 times -4, 0, 0, 3. Okay? I didn't have enough room, so I'm a little squeezed, but this is again 2 by 2 matrix, -4 and 0, 0, 3. See, indeed, when you do a cross down, this -4 only gets multiplied to the first column, right? And this 3 only gets multiplied to the second column. You get that? Yeah. Yeah. If I was teaching this in the Intro to Linear Algebra course, I would be spending much more time on this. But unfortunately, I have a lot to cover, so I can't devote that much of a time. So if you're having trouble following what I'm saying, when you go home, I want you to redo all the calculations, okay? Just make sure you redo all the calculations and see for yourselves that indeed, if you multiply this, you do get the same thing as -4 and -8. Okay? You get that? You can do that, right? Negative 4 times 1 is negative 4. Negative 4 times 2 is negative 8. So this left side better be the same exact thing, okay? Just make sure you do those calculations, all right? And then once you're done with it, you should also do this calculation and do this calculation and see that indeed, if you multiply this, you get negative 4, negative 8 as the first column, and then 9 and negative 3 as the second column. Make sure you do that. Okay? Then you're going to understand what's going on. Okay, okay. And then do you realize that this is a diagonal matrix? And we're almost there because now all we have to do is this is going to be our P. This matrix is going to be our P. So what we have is this form: AP equals to DP, PD. Right? The same matrix, A times P equals to P times D. And then you're going to multiply P inverse both sides. Of course, P and P inverse cancels out, and you get A as PD P inverse, exactly how we wanted it to be. Okay? So we have the result that 2, negative 3, negative 2, negative 3 equal to 1, 3, 2, negative 1 times negative 4, 0, 0, 3 times inverse. Okay, and we use that idea, therefore we're almost there. We have now 2, negative 3, negative 2, negative 3 to the nth power equals to 1, 3, 2, negative 1. We watched how the P and P inverse cancels inside, and you really just get nth power for this one. These don't get powered by n, those don't appear, only this one. So you get negative 4 to the nth power, 0, 0, 3 to the n, then 1, 3, 2, negative 1, negative 1. Okay. Now, in practice, this is all you need. When you're trying to do the power series, you just need to know this. You don't have to compute explicitly after this, but so this is what I consider as a fully correct 100% answer. But if you want to know further how that can be simplified more, let's walk that extra mile. So let's see. Who here remembers the inverse of 2 by 2 matrix formula? What is it? 1 over AD minus BC. Okay, what goes here? D and A get switched, then B and then C gets negated. Okay, so therefore, if we have 1, 3, 2, negative 1, inverse, that's going to be 1 over, 1 times negative 1 is negative 1, minus 3 times 2, that's negative 6, so it'll be negative 7 here. And then you switch 1 and negative 1, so it'll be negative 1 and positive 1, negate 3 and negative 2, and then, let's just multiply everything in, so it's like 1/7, 3/7, 2/7, negative 1/7. Okay? So that's the inverse. And now we're going to calculate this guy here. Okay, let's just do this part first. So you have 1, 3, 2, negative 1 times negative 4 to the nth power, 0, 0 to 3 to the nth power. Across down, it's just negative 4 to the nth power. across down, that's 3 times 3 to the nth power, which is like 3 to the n plus 1. Then 2 times negative 4, 2 times negative 4 to the nth power. If you do this, and then this times this gives you negative 3 to the nth power. And now this and this, these two have to be multiplied, so we have negative 4 to the nth power, 3 to the n plus 1, 2 times negative 4 to the nth power, negative 3 to the n times 1/7, 3 over 7, 2/7, negative 1/7. Okay? And then if you do across down, now we have negative 4 to the nth power plus 2 times 3 to the n plus 1 over 7 as the first guy, and then multiply this times this. That's 3 times negative 4 to the nth power minus 3 to the n plus 1 over 7. Then this times this is 2 times negative 4 to the nth power minus 2 times 3 to the nth power over 7. Then this times this gives you 6 times negative 4 to the nth power plus 3 to the nth power over 7. So that's the solution. And you can check whether you're correct or not by plugging in various values, like n equals to 1, 2, 3, 4. You keep doing it and you'll see. Especially when n is 0, you should be getting 0 here and 0 here, 1 and 1, because anything to the 0th power should be the identity matrix, right? So that's what you're going to see.